Thanks everyone for joining this session on advances in monitoring and modeling streambank erosion. First up, we have Layla El-Khoury from NC State to talk about geospatial and field-based methods for predicting and quantifying streambank erosion.
I think I'm going to go ahead and get started. I'm Layla El-Khoury. I'm a current master's student in the Bio and Ag department at NC State, and I work with Dr. Barbara Dahl and Dr. Jack Kirky-Fox, and also with Dr. Melanie Carter on part of my project that takes place in Virginia. And today I'll be talking to you all about quantifying and predicting streambank erosion using geospatial and field-based methods. So as I'm sure many of you know, sediment is one of the top 3 pollutants in rivers and streams, and it leads to a lot of negative consequences while the excess sediment in the water that leads to an overall decrease in our stream health. And streambank erosion can be a significant source of in-stream sediment loads, contributing anywhere from like 17 to 92%. So it's important to be able to actually measure and predict those erosion rates to help us prioritize streams for restoration efforts. A lot of times you want to identify the site that's going to have the greatest reduction in your downstream sediment. And another aspect of restoration efforts is being able to use desktop geospatial tools to help identify and narrow down sites prior to going out in the field, which will hopefully help save time and maximize limited resources. And so one of these tools is the USGS's positive openness layer, which is a raster data set that was developed for North Carolina using 2013 and 2015 LIDAR data. And it identifies the location of concave surfaces or incised streams where the relief angles are less than 90 degrees. I'm not going to go into a lot of detail on it, but Charlie and Laura will talk more about this in the next presentation. So my overall research goal is to improve methods for identifying, predicting, and quantifying streambank erosion to better target restoration efforts. So this is through looking at different methods to actually measure erosion rates. So using physical surveys, so going out in the field, setting up permanent cross sections, looking at aerial imagery analysis, and then also looking at LIDAR surveys. And then it's also looking at predicting erosion rates using the Banks method, which is the bank assessment for non-point source consequences of sediment, which was developed by Dave Rosgen, and it's composed of your bank erosion hazard index, your new bank stress, and measured erosion rates. So the Bank Erosion Hazard Index, or BHI, is represents your erosion potential for a bank, and it's composed of 7 different parameters that are either visually or quantitatively assessed and measured out in the field. You take all those parameter index scores, you add them all together to get a total BHI score. The higher the score, the higher your erosion potential, and that score is it's correlated with a BHI category from very low all the way up to extreme. The second component of banks is your near bank stress. So this represents the shear stress of the flow on the banks. And this can be computed from 7 different methods. So I'm looking at doing method 1, which is a visual assessment based off of where you are along the stream. Are you in the straight part? Are you in a bend? And also any in-stream features, like is there a mid-channel bar? Looking at method 2, which is a ratio of the radius of curvature to the bank full width, and looking at method 5, which is the near bank maximum depth to bank full mean depth ratio. So you take BHI and MBS and you combine them together with your measured erosion rates to hopefully produce a curve like this one developed by Rosgen for Colorado. And this is used for people to help justify restoration efforts. So along the bottom, you have your near bank stress categories. You have a regression line for each of your BHI categories, and then you can kind of estimate or predict what the annual bank retreat would be for your site. So all you'd have to do in the field is perform the BHI assessment and MBS assessment, and then you wouldn't have to measure erosion rates. While we were out in the field, besides applying behind MBS, we also qualified the type of erosion. So either identifying the bank as a stable bank, there was no erosion. If it had surface scour, so just kind of that top layer is being washed away by the water. If there's hoof shear, so obviously if you have any livestock that aren't fenced away from the stream, there's kind of trample the stream bank. If you have unstable undercut where the toe of the bank is eroded away and the top part of the bank is left overhanging, and then that eventually falls, leading to mass wasting. So part of my study takes place up in Virginia in the Valley and Ridge and Blue Ridge regions, where I have 15 unstable stream sites, and looking at hopefully developing an erosion curve for these regions in Virginia, as well as looking at comparing different methods to quantify bank retreat. So for each of these sites, we've completed the behind MBS assessment. We've also set up a number of permanent cross sections for 6 of our sites that are relatively open, looking at applying aerial imagery analysis to measure bank retreat, and then 3 of our sites that are in really open pastures, so very minimal overhanging vegetation, applying Lidar as well. So at each of our sites, we established anywhere from 2 to 7 permanent cross sections, depending on our reach length, which we tried to pick about 1,000-foot reach length for each site. And we tried to select cross-section locations where we thought we'd see the most active erosion. So really paying attention to where the water hits the bank. And partway through, we started including surveying the top of the eroding banks along the stream, since cross sections give you a very accurate representation at that specific location, but that doesn't necessarily give you an accurate representation along the entire stream reach. So we started applying top of the bank surveys to maybe get a more accurate reach wide bank retreat. So I know surveying undercut banks can be a little bit difficult, and it's a lot of times left out of studies. So we had 2 different methods when we were dealing with undercut banks. The first one was where we put the prism directly up against the bank, and you use 0 feet for the rod height. This works really well if your total station is obviously set up on the opposing bank and you can easily just shoot the prism. If you can't do that, then we would just measure the offset between the rod and the bank and make a note of it and then correct it afterwards. So I took our survey data and put it into Excel to actually quantify the bank retreat. So I would select the top of the bank elevation as the lower of the 2 surveys, select the bottom of the bank elevation to be the higher of the 2 surveys, and paying special attention to where I set the bottom of the bank elevation to make sure it was above like any slumped material that was at the toe of the bank that hadn't been eroded yet. Because if you include that, it kind of skews your bank retreat analysis because it looks like there's deposition. It's not really, it just hasn't been eroded away yet. And then I set a 1/2 foot interval from the top and the bottom of the bank elevation. I did a linear interpolation to get the station for each of our year surveys, subtracted the 2 years from each other to get you bank retreat. Anything that was negative represented erosion. Anything that was positive showed deposition. And this is just an example summary of one of the cross sections of Sinking Creek up in Virginia. You can see the left bank has more erosion in the picture, and it also shows that there's more erosion from the bank retreat analysis. So taking all of my behind MBS data, along with all of the measured bank retreat rates, I'll work on developing erosion curves for the Valley and Ridge and Blue Ridge regions of Virginia. I'm going to look at statistically comparing all of the various banks variables to bank retreat. And then I'm also going to look at adding additional explanatory variables to increase the prediction. So looking at Simon's channel evolution. So this takes into account where this where the stream currently is. Is it in a place where it's actively eroding, or is it done eroding and starting to erode? And then other factors like the stream size and watershed area. I'm also applying aerial imagery analysis following the methods by Purvis and Fox, where you trace the top of the bank, join bank lines together, convert the polylines into a polygon, join polygons together, remove the middle section, determine if the remaining polygons represent erosion or deposition. You can calculate the area from that. And to get the volume, multiply the area times the measured bank height in the field from B high. And the last method for measuring bank retreat is using Lidar surveys. These were completed by Withers and Ravenel for our 3 sites, and then I'll be using the geomorphic change detection software to quantify the amount of erosion and deposition. So moving on to the last part of my project, this is in Mine Creek Watershed, which is in North Raleigh. And this part of the project is looking at validating the positive openness layer. Is it accurate at identifying where there's erosion? So for this watershed, we picked it because it had the most erosion complaints in Raleigh. And that was one of the factors we were trying to see if erosion complaints could be used to indicate where erosion is. We also tried to select sites that covered a range of stream sizes and a range of the positive openness signal. So using the 3-meter positive openness layer, I visually quantified the positive openness signal, where obviously there's no signal, all the way up to high signal, which is supposed to indicate a high degree of incision, so hopefully a lot of erosion. So we ended up picking about 54 individual sites where we went and applied the behind and BS. From those individual sites, we picked 7 of the worst sites. You can see one of them on the top 2 pictures, where we set up permanent cross sections to measure and then resurvey a year later to compare the values to the North Carolina erosion curves. We also selected 3 stream reaches to perform a B-high reach analysis and look at the accuracy of the positive openness layer along an entire reach. So really quick, some preliminary results. As you can tell, using complaints to see if you have erosion is not the best method. But if we come down below, you can see we had some false negatives and some false positives. A lot of the false positives where you had a really high signal but no erosion out in the field was due to the fact that these were smaller streams that were in a really steep and deep ravine. So the signal was more likely picking up on the actual ravine rather than the stream banks. I got the 1-meter resolution positive openness layer from USGS and have been doing some preliminary analysis on it. And the highest correlation that I was able to find between the positive openness signal and the various factors I was looking at was the type of erosion that we qualified out in the field. So obviously where you had no erosion, you expect it to have a higher positive openness signal, so less incision. And for the more severe types of erosion, unstable undercut, mass wasting, you have a lower signal. So I also found the same trend for all of my reaches. And this indicates that the positive openness layer can be used to kind of identify where you see erosion and then where you wouldn't see erosion. So any questions?
I don't see any questions in the chat, so any questions in the room, feel free to answer. All right, if there's no questions, we can just, go ahead.
Okay, Layla. Where do you think the positive openness, that tool may be perform better? Do you think it's going to be the same in all watersheds, or do you think there's other watersheds that may perform better in?
So probably will perform better in a watershed that's more alluvial versus the water. So Mine Creek watershed, it's not as alluvial as some other watersheds. You have a lot of the streams you went to, there was some more bedrock in the stream. So maybe applying it in a watershed, in a watershed where there's more alluvial material and could result in sorry, can't think.
All right, well, I think that's the end of this session. Thanks everybody for coming and bearing with us through some technical difficulties with the combination of virtual and remote, so virtual and in person. Thanks everybody for sticking in there with us. I'll stop sharing my screen. You don't need to watch this loop through a million times. All right, thanks. Thank you. Have a great day. Bye.
Everyone, that concludes the session.